I want to actually move on
Sure.
to another research topic that you had, because it also ties into the problems that we're facing today, and this is parallelization.
That's right.
So you did a fair bit of research and publishing at NVIDIA on parallelization, which tackles another aspect, or which associates with other aspects of the kinds of problems that we're facing today as an industry, as we try to realize, as you mentioned in your last answer, as we try to realize as an industry value from these extremely expensive capabilities, systems that we're developing and deploying.
Yeah, parallelization strategies, I think they kind of fall into that category of coming up the layers of abstraction from kind of microarchitectural improvements to like system aspects to just pure software. How do you best make use of large amounts of compute that you have available to you? And that particular body of work was at a time where, and I think it continues to this day, where there's a lot of effort that goes into how to make best use of thousands, tens of thousands of GPUs to reduce the both power, cost, and time that goes into training a new model. And one of the really interesting aspects at that time to me was the various different modes of parallelization that people had started looking at. At that time, data parallel was probably the main thing. Model parallelism had just started becoming something people were looking at. I think the paper that you were referring to is where we were looking at the different kinds of model parallel, one being kind of the traditional model parallel, and then pipeline parallelism. After that, tensor parallelism has been kind of added to the mix. And there's entire startups that focus on how to best implement these various parallelization strategies with some really great impacts, because even tens of percent improvement there at the scale that we're talking about means a lot of money and a lot of energy that's really important in this problem. But one of the interesting things is that these were all problems heavily focused on the training side. And when we think about who all in the world is doing training in large scale from scratch of the models, it has significant impact, of course, because just from an energy consumption perspective, right, and the fact that we're always improving these models, like very big problem. But as we've kind of come into the space where now there's a lot more use of the models being defined and actual prediction tasks and building applications, the inference side is also the place where you think of where compute is going to be used most in the next 10, 20 years. It's likely that most of the compute is going to be inference compute. And so that's where I think that particular piece of research that you're referring to, I think of that as one of the places where a shift for me started happening of, again, from the hardcore, we're improving performance for the most compute intensive tasks, which at the time, training was the main thing. In fact, there was a back and forth between whether training of large language models was the most compute intensive task that we spend our time on thinking about, or large recommender systems. Also, back then, it wasn't, as a researcher in that field, I was looking at both of those problems. But now, looking back 4 years ago, that's where most of my interest was. That interest started shifting around that 2019, 2020 timeframe to thinking about, what about inference? How do we scale inference, and how do you have efficient compute delivering all of that, which is tied to some of what we just talked about.
Yeah, and so now you mentioned earlier Llama 3.1 405B. You might have a better sense off the top of your head as to how many kind of state-of-the-art NVIDIA GPUs would be required to run a model that large at inference time, but it will be multiple.
Yeah, it's 30. I believe if it's running in its baseline capacity, it's 32 H100s.
Wow.
So you need 4 boxes of GPUs to even stand up one instance of it.
Right.
One instance. So if you're thinking of doing any sort of fine tuning of it or trying to serve a lot of different users. Now you're talking about multiple of that in order to be able to get through fine tuning, for instance, in a time efficient manner. But yeah, that's where you start understanding kind of the complexities around maintaining those systems is why it's not trivial to think that everybody's just going to do this for themselves, even though it's doable theoretically, right? There's nothing stopping you from going and getting 32 GPUs somewhere on the cloud and trying to stand this up. But how quickly will you have a production ready system for that? I think sometimes gets underestimated a little bit.